Just 1 minute, we can start recording. Yeah, I think it's recording. Okay. So what is peak to average power ratio? Okay, so if you take any signal, essentially, this is how your signals will look. Okay, so essentially peak to average ratio. So there's an average power, and there's a peak power. Okay, so this ratio matters. Let's just take 5 minutes to discuss why this peak to average power ratio matters. Okay, so to do this, we should understand the power amplifier. Okay, so we have the power amplifier. Okay, I mean theoretically power amplifier. What does it do? Give it x of t, it gives y of t, where y of t is a scaled version of x of t. Okay, so the power in y of t, that is y of t whole square, will be alpha times the power in the y of t. I mean y of t will be alpha times expected value of x of t whole square. Okay, so depending upon your amplifier, alpha can be 10 dB, 20 dB, 30 dB. Okay, so this is a theoretical model where whatever value of x of t you give, you get y of t. But in reality, what happens is, so if this is the input power and this is the output power. Okay, how does the curve look? The curve goes straight for some time and then starts bending. Okay, and afterwards it saturates. Okay. So the first point at which there's a 1 dB gap between the linear, I mean, if you just do a linear interpolation from the bottom, this is how the ideal thing, you want the ideal thing to look. Ideal curve. Okay, this is an actual. Okay, the first point at which is a 1 dB deviation from the actual is called the P1 dB, referred to the input. Okay, P1 dB compression point. It's called P1 dB compression point. There's something like this called P3 dB, also P3 dB compression point. Okay, so what you want, so if you talk about OFDM wants linear region, because see, if FFT you take and you square the FFT, okay, it will expand in the frequency domain, you will not be able to decode it. Okay, so what you want is, you want the signal to operate in the linear region. So you want the signal to operate in the linear region so that there are no non-linearities because of compression. Okay, so what you do is, if you suppose you operate at this point, this is the average power at which you operate. Then what happens? There's a swing on the signal. The signal is not a sinusoid wave. Right? It's not a pure sinusoid wave, or it's not a pure DC wave. It's not a pure DC. There is some swing because that's where your information encoded. Okay. So what happens is, if this is your average power, your peak power sometimes might hit this point on both sides. Okay, this is the peak power. Okay, so what you want to do is, you want to operate so that your peak power is less than the P1 dB compression point. Okay, so essentially what you want to do is, you want peak power to be less than, less than P1 dB. Okay, I'm putting P1 dB, but generally you put something less than P1 dB, because already at P1 dB you are compressed. Okay, you want to put it less than P1 dB. Okay, so, but if you think about it, what is the actual transmit power that happens? The actual transmit power is, the TX average power is average. Okay, so this average power in some sense dictates the range that you get, and the peak power in terms of peak power is the one which you should back off from your P1 dB, so that you do not have non-linearities. Okay, so what is the take home thing from this? If your peak to average power ratio is greater, then your back off will be higher. Okay, so if your back off is higher, there are two problems. One is, of course, your transmission distance decreases because the average power is decreasing. And second thing is, you also operate the PA at a lower efficiency. The lower you go here, the lower the efficiency becomes. Efficiency of the PA becomes. Okay, so this quantity called the peak to average power.
Sir, what do you mean by the back off power?
Okay, so this is the back off power.
Means the range of swing is, you want to say back of power.
Range of swing, in some sense, range of swing. Okay, so essentially what I mean by peak power, let me define this properly. Okay, peak power is, so suppose you have a signal, discrete signal. Let's just talk about discrete signal. So you have a signal x of n. Okay, so this is your wave formula. You will have x of, for n is equal to 0, 1, 2, so on up to infinity. I mean, this is the signal that goes on coming. Okay, so peak power is max of mod x square. Okay, average power is the mean value of expected value of mod x square. Okay, you can define this also in terms for the continuous time signals. So I'm just doing it for the discrete thing. So your PAPR will be equal to max of peak to average power ratio. Sorry. Okay. So what this means is, if PAPR is large, what it means is the maximum is large compared to the average. When that happens, what? This swing will be larger. This swing will become larger. Since you don't want the swing to cross the nonlinear point, what you do is you decrease the average. I mean, you decrease the average transmission power. You scale the entire signal by some beta so that the entire average power decreases. Okay? Does it make sense? Okay. So why is a PAPR problem high in? Why is PAPR large in OFDM? Okay, the answer is very, very simple. What is your time domain signal? Your time domain signal y of n would be equal to sigma x of n e power minus j 2 pi, what is your time domain? Y of k, kn by capital. Okay, this was the IFFT, na? N is equal to 0 to n minus 1. Yes? So what effectively is happening is, you are taking a lot of signals and adding them up. Lot of complex signals are adding up. So when this happens, what happens is, effectively, I mean, I don't know if you have heard of law of large numbers. What does law of large numbers say? I mean, law of numbers, central limit theorem. Okay, not law of large numbers, central limit theorem. What does it say? You add a lot of random variables. You add x1 plus x2 up to xn, lot of equal random variables. This converges to a Gaussian distribution. Okay, this converges to a Gaussian distribution. Okay, so how does a Gaussian look? Gaussian will have a lot of spread. Okay, with certain mean and certain variance. Okay. Now, if you look at this, this is also sum of large number of signals as your n becomes larger and larger. Okay, and x of n is anyway random because that depends on your data. Okay, so effectively, so y of k looks like a complex Gaussian. Okay, so what is the PAPR of a Gaussian? Can anyone tell me? Of a theoretical Gaussian distribution. What will happen? Gaussian goes all the way to infinity, na? So the PAPR of a Gaussian is infinity. Okay, the mean can be anything. Mean can be anything, but the maximum value of a Gaussian random variable can be infinity. Okay, but in practice, you will never get infinity because you are power limited and other things. I mean, it just effectively looks like a Gaussian, but it's not theoretically, technically Gaussian. Okay, so it implies y of k has large PAPR, peak to average power ratio. Okay, so this is one serious problem of OFDM. So essentially, because you are making your output signal is nothing but a sum of a lot of input signals, lot of input data, weighted data, complex weighted data. What happens is y of k effectively looks like a Gaussian. You can compute the mean, you can compute the variances of all this. Okay, you can do all that. Okay. So what is going to happen is, because of this, the PAPR will be large. Because the PAPR is large, what you have to do is you have to do, and the OFDM does not play at all well with non-linearities. Because of that, you have to back off. Because of that, you have to back off. Okay, so this is an issue. There are multiple ways of getting over it. I will not talk about that today. Okay, I mean, those of you interested, we can have a separate session on this PAPR alone. But I want to point out two things. One is PAPR increases with increasing N, increasing subcarriers. 2. PAPR increases with increasing modulation. What I mean is, so x of k in this expression, the x of n comes from m quam, na? some quam modulation. As m increases, PAPR increases. Okay, does it make sense? Okay. Typically in 5G, depending upon the modulation and other things, in an OFDM system, cyclic prefix OFDM, the PAPR is about 8 to 10 dB. Okay. So essentially, effectively, what this says is the peak value is greater. The peak power is about 10 dB more than the average power. Okay, so your back off should be about 8 to 10 dB in a OFDM system. But one thing you can do is you can actually compute what is the PAPR. You can actually compute what is the PAPR in the OFDM signals that you're generating. Go to generating your assignment. Okay, because we know how to compute. You have to take the maximum value and you have to take the mean value and take the ratio. Okay, you can compute this for different QAM. Fine. So, any question before we proceed?
Sir, this is Shubham here.
Shubham, please.
Sir, I had one question. You said that with the increasing order of modulation, we will face a higher PAPR.
Yes.
And it's true for QAMs. I mean, is it because because higher the QAMs, the symbols are even more energy dependent?
No. See, higher the QAMs, essentially what happens is, essentially if you look at this is a summation of multiple terms. Huh? Higher the QAM, X of n randomness also increases.
Okay, so it's true even for if we not go for a QAM and say we go for some sort of a MPSK symbols, even then it's true.
Increases with P, increases with whatever M. Okay.
Okay.
But what is the relation? I mean, what is the relation between MPAM and MQAM? That you have to do by simulations. PAM will have a lower PAPR in general than QAM.
Okay.
Sir, is it not because of higher power required in higher order of modulation, PAPR?
No, PAPR has nothing to do with the power.
Okay.
PAPR is a ratio, no? So the power. So even if I scale my x of n with some beta is there on the top and beta is there on the bottom. Okay, so that will not.
Okay.
So it depends on the structure of your modulation and the number of subcarriers.
Okay.
Sir, is it true to say, say the more the amount of randomness in our symbols, the more is the possibility for a PAPR to go high?
In some vague sense, yes. I mean, I don't think that's a very accurate statement, but yeah, that's a rough intuition.
Okay.
See, essentially, the more Gaussian it becomes, the more PAPR you have. Simple. Okay, Shubham, that does make sense?
Yes.
Okay. You can actually theoretically compute the PAPR. I mean, those of you interested, you can actually think of this as Gaussian, find the mean and the variance, and from the variance, approximately, you can say that 3 sigma will be your max. Okay, and anyway, how it scales with n, you can find out.
This is VK Roy.
Hello, sir.
In SCFDMA, we reduce the PAPR, but I think the multi-carrier nature increases the possibility of PAPR.
Yes, there is a multi-carrier nature. See, it's the multi-carrier where you are doing a summation. See, in single carrier, you don't do this. Na? Single carrier will be y of k will be x of n, where x of n is modulation.
Right.
So whatever is the PAPR of, we didn't do pulse shaping, but if you do pulse shaping, it will be a little bit more than the modulation. That's all. But
Right.
here you're summing it up. That's what exactly is the reason, sir.
Okay.
Okay. So single carrier FDMA looks like a single carrier SCFDMA, almost like a single carrier, because the FFT effect will go away. Okay. That's why it decreases the PAPR. Okay, good. So saying this, I mean, now almost all the systems ubiquitously are using OFDM. Okay, I mean, you take most of the system, Wi-Fi uses OFDM. What do you say? Cellular systems who use OFDM, digital video broadcasting uses OFDM, DSL modems who use OFDM. So now the PAs are also built in such a way that they can handle this OFDM. Okay, and the back off, depending on how much aggressive you are, they can look at multiple techniques to reduce this PAPR. Okay. So while it is a problem, specifically in very, very high power systems, so what happens is in very, very high power systems, this non-linearity becomes much more prominent. The more higher power you go, the non-linearity becomes that much prominent. So in very, very high power systems, people generally don't use OFDM. For example, you want to do space communication, okay, where you have to, because you want to send, signal to satellites or send signal to Mars rover. 10 dB is a lot of power to waste. Okay, so in Mars rover and other things, what they do is they operate the PA at effectively this point. Okay, so you require waveforms which are very, very resilient to non-linearities. Okay, so that's what they use single carrier FSK modulation. Generally, FSK modulations are frequency shifting modulation, like GMSK. GSM is a very, very good example where you can drive almost the PA to the saturation and still works. Okay, the main reason is because it's in frequency. I mean, the modulation happens in terms of phase and frequency. Okay, so they use some waveforms like that to actually operate the PA there. Okay, they use something, they do some other masala. I mean, that's for some other class. But so generally, if you are power limited, you want to operate at this point because you want to push out as much power as possible. Okay, but in cellular systems, we are bandwidth limited, more or less. So bandwidth is more expensive. Okay, so you generally operate lower, but you make sure everything is linear. Okay, that's what happens in general. I mean, this is just a trivia point to keep in mind. Okay.
In frequency, in FSK, we are changing the frequency or phase as per the requirement.
Yes, sir.
So why don't we just a possibility I would like to ask? We can have some QAM type of thing in FSK also, changing frequency, some QAM or something more than once we can change the phase and all, and same thing could be detected. So there aren't be any problem of PAPR. What is your observation? What is your comment, rather?
Yeah, let me tell you my comment. So GMSK, for example, GSM uses GMSK, na? Let me just GMSK. In GMSK, what you do is you do frequency modulation or phase frequency / phase modulation, what you call phase modulation with MQAM. But M is 2 QAM, 4 QAM, I mean, sorry, BPSK, 4 QAM, 16 QAM, I think maximum. Okay. So I mean, I think you remember pi by 2 BPSK, na?
Right.
Pi by 2 BPSK with SCFDMA looks approximately like, I mean, you can do the math, it looks approximately like phase modulation. Okay, that's why it has a lower PAPR. I mean, actually, this motivation for this pi by 2 BPSK with SCFDMA came from GMSK phase modulation. I mean, there's something called Laurent approximation. Okay, so both of them look the same. See, technically you can use, but GMSK has problems in terms of multiple access and other things. Okay, see, OFDM, we have a nice time frequency grid now where we can allocate users and other things. GMSK, it's not like that. Frequency division multiplexing is very painful in GMSK. That's the main problem.
But I think more research is required in this field.
Yes, sir. I mean, there are lots of problems.
Because dependency on the amplitude, that is, I think, the limitation with the PA and all, that can be removed if we have more research on this and use the FSK and all.
Yes, sir. So new waveforms is a big topic of work that has to be done.
Right. Okay. Thank you.
So with this, I'm going to close OFDM. I think we had about a week to 2 weeks of OFDM. I'm hoping that all of you understood some basics of OFDM. Okay, there's a lot more to read. I gave some textbooks also. I'll also put more material. Those of you interested can read. So in general, when I teach a digital communication course, there are special courses on multi-carrier modulation where we just teach OFDM just for the whole semester. Okay, we go into a lot more details on the spectrum, we go into power loading and other things. Okay, but for us to understand the standard, this much is sufficient. Okay, I mean, at any point in the standard we require more, I will teach at that point. So I think now we have already almost finished about the whole of February. We are talking about the basics of digital communication, frequency times and other frequency and time nothing. I think now what we will do is we'll switch gears and go into the standard. Okay. So while teaching the standard, I will also start, I mean, at points where we require to understand more about digital communication, I'll teach at that point. Okay? I want to go in that way because otherwise we'll also get delayed. That's another issue. More than that, yeah, I think it's a 5G course, so we should start 5G. Okay? So today we will start 5G. So before I start 5G, I think first thing that I'm going to talk about is the documents that are required to understand the specification. Okay. I'm going to switch to Google Classroom once. So in the Google Classroom, in the books and documents, there's something called pre-GPP specs release 15. I think Ashwati, what she did was, Ashwati downloaded the latest release 15, I think 15.8 if I'm not mistaken. And she converted them to PDF and put this as compressed archive. You can download them. You can just click on open in a new tab or something and download them. Yeah, I was able to download them. Okay. So if you uncompress them, you'll have these three folders: file layer, radio spec, and RRC. I mean, it's very small. Let me just increase the font. Yeah, I mean, so the three things: file layer, radio spec, and RRC. Okay. So what are the documents that are there in this? Okay, there are three sets of documents. So physical layer, as you know, physical layer talks about the actual physical layer, the modulation and other things. Okay. So there's a bunch of documents. We'll go through these documents in a minute. And there is one folder on radio specifications. This radio specification mainly talks about the transmit power, the spectrum, the frequency allocation, and ACLR. I mean, what is the quality of reception, quality of transmission, EVMs. That's what the radio specification talks about. And there's another important document called RRC specification. Okay. RRC is nothing but radio resource control. So this is a signaling specification. Okay? So we are going to use all these documents in our class in some way or not. Okay. So we are going to there are some documents which are very, very simple and just introductory documents. We'll go through that today. But more or less, we are going to use all these documents, most of these documents, and some of them more than the other. Okay. For example, 38331 is something that we use extensively. Okay. And the reason why I am giving a PDF file is doc files take a lot of time to open. Okay, and we have converted them into PDF files, so that's easy to open. And all of us, let's use the same set of specifications because it's easy. I mean, because between versions, there's going to be some small changes. It will confuse each of us if we use different specifications. So let us use the same specification. And one thing that I'm going to do a lot of places. So for example, I'm just going to open up some document. So you should also have a good PDF reader, whatever it is. I mean, Adobe is fine. Adobe Acrobat is fine. RRC protocol 38331. Okay. Okay. So we're going to do a lot of searching. Okay. For example, SSB. Okay. I mean, there are lots of IEs that are going to search. They're going to take time, and we will look at these IEs and other things in great detail. Okay. So please make sure that you have a good PDF viewer and which can search. Okay, that's the only way to learn the spec. I mean, SSB is a very bad idea to search. Okay, so so one more thing that I want your help is I'm going to open the spec documents quite a bit. Okay, and sometimes I'll forget to zoom them. Please let me know if you're not able to see the spec document that I'm doing. It's clear, not clear. Please let me know. Okay, I'll try to remember to zoom everything. But if in case I forget, please let me know. Okay. So now I'm going to use the spec documents quite a bit. Okay, so it may be good to open them in your laptops also and keep them ready. This whole folder. Okay, from next class onwards you can do that. Download all these documents first. So from now on, I'm also going to use a set of slides also in addition to what I write, because a lot of these things are pictures and other things that it's very difficult to draw sometimes. Okay, So let's start with the 5G thing. Okay, I'm just going to remove my notes 1 minute. Okay. So all of you can see my screen. Is it clear enough? Shubham, can you see my screen? Is it clear?
Yes, it is clear, sir.
Yes, sir, we can see.
Okay. So the first thing that you remember, the first thing that we have to do is these are the set of documents, and these are the documents that we are going to use. Okay. So all the documents of of 5G start with the number 38. Okay. 38 is the series for 5G. 36 was the series for LTE. Okay. So any document that starts with 36 is technically an LTE document. Okay. This is more or less a thumb rule. And any document that starts with 38 is a 5G NR document. Okay. So that's why 5G is called a 38 series. Okay. As I said, there are documents, the 2 series documents. So if you look at the physical layer documents, they all start, the next number is 2. 201, 202, 211, 212, 213, 214, 215 are the physical layer documents. They are the RAN 1 documents. Okay. So RAN is the radio access network 1, which in 3GPP talks about makes a specification for the physical layer. Okay. So 38.211 is a physical layer document. 38.215 is a physical layer document. Okay. So anything with 38 is the 5G, and the 2 part is the RAN 1 or the physical layer part. Okay. 38.1, anything that starts with 38.1, 101, 102, 103, 104 are the radio documents, are the RF documents. Okay. They are made by RAN 4. They are made by RAN 4. Okay. Sorry, this color coding is a little bit off. And 38.3 are the radio access controller, MAC controller, which are made by RAN 2. Okay. So that is how you identify which document belongs to which group. Okay. So 2 stands for physical layer, 1 stands for RF layer, and 3 stands for RRC and MAC. Again, this is a standard convention that people follow. Fine. Okay. And how do you get these documents? You can get these documents by searching in Google. Okay. Sorry. You just type 38.201. Okay, and you can go to 3gpp.org. Okay, you can go, you can click on the versions. In the versions, you will see different releases, release 16, release 15. Okay. And this in this release also there will be multiple updates. So for this particular 38.201, there's only one document, version 15.0.0. You click on the version, you'll be able to download that file. Okay. So let's just do this one more thing so that it's, I want people to be comfortable, the students specifically. You can click the document. Okay. You can go to versions. See here you see the 15 release has multiple, 15.00, 15.123. So whatever we have downloaded, I think what Ashwati downloaded is 15.8.0 in that folder. Okay, so you click on the version, you download that file for you. Okay, as a doc file it downloads. Fine. Does that make sense? You can also get all the change requests for that using this. It will take some time to load this. Okay. You can open this, more TDoc. TDoc is the working document for 3GPP. Okay. So it tells you what is the working group agreed document, what is the RAN plenary agreed document. All these documents can be opened upon. Okay. You can also get more details by clicking on this TDocs. Okay. You click on the TDoc. We're also going to use a lot of TDocs also in our class. Okay. Anyway, we'll do that later. It will take time for us to know. Okay. So you can get all these documents from Google, this thing. Right? Anyway, for making it life easy, I just downloaded all of them and put them in the classroom so that all of us use 15.8.0. So we are going to use release 15.8.0 for this class. Okay. So did you understand the document structure? Any question? Is it fine? Shall we go ahead? Okay. No. So the next. Okay. So in this course, I'm going to focus mainly on the radio part of the network. Okay, I'm going to teach a little bit about the MAC and RRC later. Okay, RRC will use quite a bit. RRC will use quite a bit in this class, but our focus mainly is about the physical layer. Okay. So the first document in the physical layer is the 38.201. Okay, let's open the 38.201 and start understanding how does the document look. So I'll go to the physical layer. Okay. So just to give you an idea, so it says the version number. It says 38.01 technical standard. Okay, and the next part is it generally has the contents, table of contents. Every document has this, followed by the scope of the document. Okay, the first part will always be the scope of the document. What does this document contain? Okay, so what does this document contain in terms of what do you say? In terms of details, okay, followed by all the references that is using. Okay, every document has the same thing. Okay, any 3GPP document you open, this will be the same thing. Okay, a lot of abbreviations are okay. So let us first start understanding what are the different layers and what is the relation between these layers. Okay, let's start reading this up once. Let's just read up a little bit. Okay? I would encourage you to read this. I'll just wait for a minute, and then I will describe this. Okay. So what this diagram is saying is, what is the relation between the physical layer, the MAC layer, and the radio resource control layer? Okay. So we will generally talk about physical layer. So medium access control layer is the layer which actually gives the data to the physical layer. Okay. How it gives the data is through something called the transport channels. Okay. So medium access control talks to the physical layer through something called the transport channels. Okay. And similarly, medium access control layer talks to the higher layer, something logical channels. Anyway, we are not worried about that. So let's just focus on this transport channels. Okay. So this is what happens between the layer 2 and the layer 1. Okay. The medium access layer control talks to the physical layer through transport channels. Okay. So then this document goes on to describe what is the services that the physical layer provides to the higher layers. Okay. So the physical layer offers data transport services to the higher layers. These access to the services through the use of a transport channel in the MAC sublayer. Details are specified in the MAC documents. Okay, but they are generally giving a high-level description of what is there. Okay, I'm going to skip all this. Okay, we can just go through this once. Okay, so let's since this is the first document, I'm going to read this a little bit. So this is a very high-level description. The MAC, the multiple access scheme, is based on the physical layer is based on orthogonal frequency division multiplexing with a cyclic prefix. For uplink, you can also use discrete DFT spread OFDM. Okay, and CPU OFDM is also supported. Both FDD and TDD are supported. So it's just giving a high-level general description of layer 1, which is the physical layer. Okay, it also talks something about the radio frame and subframes and other things. We're going to go through this in detail in another document. Okay, so this is a very high-level descriptive document. Nothing is there in this. Okay. So it talks about what are the different channels that are there in the downlink. Okay, so this is something that's important. Okay. What are the channels that are there? There in the downlink, there is first thing is called the physical downlink shared channel. Physical downlink shared channel. That is the main data channel. Okay? Shared channels are always the downlink. Shared channel means the main data channel. Okay? The downlink control channel is where the control information goes through. That's called the PDCCH, physical downlink control channel, PDCCH. Okay? And the last channel that is there in the downlink is the broadcast channel. Okay, this is where the general cell information goes in, the synchronization signals go into PVCH, broadcast channel. Okay? Uplink also has 3 channels. Again, there is a shared channel. The shared channel is the main data channel by which the UV transmits data to the network. Okay? Similarly, they have an uplink control channel, which is the PUCCH, which is the control information. The UV sends the control information and the scheduling information to the uplink control channel. And there's something called the random access channel. We'll go through this. This is the first channel that the UV uses to lock onto the network. Okay? And again, they talk about what are the different modulation schemes that are supported in this. Okay? This is a standard. High level, they also talk about the channel coding. They say that the LDPC codes are used for the data, and the polar codes are used for for the broadcast channel and the control channel. Okay? These are called the channels. Channels are actually the paths in which you transport data. Then there's something called procedures. Okay, so what does the spec do? Spec specifies channels and the procedures. So what are procedures? For example, when you switch on your cell phone, what is the procedure that should be followed by the UV so that it can go lock onto the network? That is called a procedure. That's called a cell switch procedure. Okay. There's similarly something called power control procedure for the UV. Okay, so it tells exactly the set of steps that has to be followed by the UV to change its power. Okay. Uplink synchronization, uplink timing control. This is called a PRACH. I mean, this and the other one are both called the PRACH, random access related procedures. HARC, hybrid ERQ. This is a retransmission protocol procedures. Okay. And the beam management and the CSI related procedures, channel state information related procedures. Okay. So all these procedures are also described in great detail in the specification. Okay. We look at all these things. So effectively, what the spec does is, spec always defines only the transmitter. Always remember this. Specification only talks about the transmitter and never about the receiver. Okay? Specification is always talked about transmitter, and specification is always written in terms of the UV. It's never written in terms of the base station. Always say again, this is the second point that you should always remember. Specification, the way 3GPP specs are written, is always written in terms of this is what UV does, this is what UV will calculate, this is what UV is going to decode. Okay? It never tells base stations to transmit this. Okay? That is how the spec is always written. Okay? So the 2 points that you remember is, it always specifies what is transmitted. It never talks about the receiver under any circumstances. The second thing it does is, it's always UV centric. It tells, okay, UV should do this measurement, UV should lock onto this, UV should do this, UV should do that. It never tells base station should do this. Okay? That is where the spec is written. It's always UV centric. Fine. Any questions before we proceed?
Whether this is true about this particular specification or it is about all specification that
I'm talking about 3GPP specifications, sir. Even 4G also is written that way. Okay. In general, all the COM specifications are written only for the transmitter, never about the receiver.
No, but in many cases that base station is also transmitted, no? Because
yes, base station. But the way they write it is, they write it in terms of the UV.
Okay.
Okay. And you have to interpret what the base station does.
Okay.
Okay, but it's pretty, I mean, it's written that way, but it's very clear what the base station has to do.
Okay, thank you.
Okay. So this is a very important thing. So this is 38.201, which was an introductory document. So this gives an overview of all the documents for physical layer, what they do and how are they related to each other. Okay. So there's something called 38.202, which is again a very small document, about 3-4 pages document, which talks about what are the services that the physical layer provides to the higher layers, which is the MAC in this case. Okay, how does it talk to the MAC layer? Okay, it tells that it takes transport blocks and processes and transfers back and gives back transport blocks. Okay, that is what's 38.202 specifies. Okay, 38.212, which takes directly information from the higher layers, is the multiplexing and coding. Okay, this is where channel coding, LDPC decoders, LDPC encoders, polar encoders are defined in 38.212. 38211, which is the most important document from our perspective, talks about the physical layer, actual physical. It talks about the modulation. It talks about the reference signals. It talks about the control channel reference signals. So all the things that are related to actual modulation and physical layer are there in 38211. Okay, this is the document which we are going to spend the most amount of time. Okay, so 38213 is called the physical layer procedures for data. 213 talks about the physical layer procedures. We saw what are procedures, self search, power control, uplink synchronization. These are the procedures. What are the steps that you have to do? Okay, so 38213 talks about the procedures to encode and decode data. Okay, 38214 talks about the procedures for the control channel. Okay, so these two documents are the procedural documents. And there's one more document which will not talk about too much, that is called 38215, which talks about physical layer measurements. Okay, so what are physical layer measurements? So for example, when the UV transmits something, the base station should understand how much power it is transmitting, so that it can do power control. So that's a measurement. Okay. Similarly, the UV should do a lot of measurements in terms of channels and other things. Okay. So all those measurements are specified in 38215. Okay. And these links tell you what documents what documents are related to what other documents. Okay. So in general, 38215 is not referred to all the other documents. It's referred to only by the higher layer documents. Okay. Whereas 38211 talks about a lot about 213, 214, 38212 talks about 213, 214, and so on and so forth. Okay. So this is a higher. What do you say? I mean, just a high level diagram which tells about what document talks about what. Is this fine?
In the diagram, there is some circle between two layers, right? And it defines that it is service access point.
Services provided to the physical layer.
So, are there any kind of software or what? I mean, service access points are.
No, these are not software.
It?
These are not software. So essentially, this tells you, I mean, so how should the data come from higher layers to this? Using something called transport blocks.
So they are just abstraction, right? They are no concrete.
Logical. It is logical.
It's logical. I mean, it's not like a software.
Not software. It's logical. Logically separate.
Okay. So 38201 is this document. So essentially, the scope. I mean, now he's going through each document and telling what it does. 38202, sir. You can read this part. Okay. Essentially, to specify the services and functions of the physical layer. It's a very high-level document. There's nothing in there. Models of the physical layer of the UV, parallel transmission of simultaneous physical channels and SRS, measurements provided physically. It's again a high-level document which describes what the physical layer is going to do and what are the services that the physical layer is going to provide to the higher layers. Okay. 38211 is the main document which talks about how do you modulate, how do you generate the OFDM signal, how do you do patch, what are the reference signals, what are the synchronizing signals. All these things are specified in 38211. 38212, which talks about channel coding, rate matching, uplink transport channels and control information, downlink transport channels and control information. So this 38212 is a document which mainly talks about bit processing. 38211 talks about symbol level processing. Effectively, this is a logical thing I'm telling you. Okay, thumb rule. 38213 talks about physical layers for control. Okay, it talks about synchronization procedures, uplink power control, random access procedures, and UV procedure for reporting control information. 214 talks about the downlink procedures for data, power control, shared channel resource. I mean, what are the procedures for the downlink shared channel, which is the data channels, uplink shared channels, which is the uplink data channel. Okay, and 215 talks about the measurements. Okay, so this is what this document is about. And again, they have see at every end of every document is also something called a change history. Okay, this tells about what documents, what input contributions in terms of TDocs are used to make these documents, along with the dates that they are doing. This is fine.
Okay. This is corresponding to the CR change request.
Not CR is a change request, sir. TDoc is the technical document. Okay, So CR happens once the document is frozen. If there is any change that has to be made, you do doing CR. But generally, TDocs make up this thing.
Here also we are changing. Change history means we are changing something day by day. So
then CR will be there.
that is corresponding to the CR or is different thing.
That will correspond to the CR, sir. If there is some changes to the established document, CR will come. In some of these documents, you will see the CRs are there. Okay? Because this is the initial document, there's nothing in this. People haven't changed anything from 15.0.
Right. But then okay.
There's nothing that's changed here. Okay? So all of you understood what are the different documents that are there. Okay, what does the document do? Okay, this will become clear. I mean, I don't expect you to remember all this. But the general thing that you should remember is 38 series is what we are going to do. 2 series, 38.2 series is the physical layer, 38.1 is the RF, and 38.3 is the MAC and the radio resource control channels, channel specification.
Sir, sir, what about the in-between numbers, that is the 203 to 2010, they are meant for something else or?
Nothing. I mean, I don't know how they chose this number. So this was, so for example, 36.211 is the physical layer, physical channels and modulation for LTE. I don't know why they started. I mean, they gave, I think everyone started after 10 bits. I don't know why. I'm not very sure of that. There's nothing called 203 up to 210.
Okay, okay, sir.
Okay. Okay. So in the slides, what I do is, generally in the slides I give you and other things, whenever I take something from a specification, I put the specification number in orange, either here or in the top. Okay. So this is with reference to this was taken. I mean, this is through the document 38.21. This is just now what we saw now. This is what we saw just now. So now let's start looking. Sorry. Can you see this diagram?
Yes.
So this is what I was talking about. So there are 3 transport channels: control channel, broadcast channel, and downlink share channel. Okay, these are the transport channels. And there are physical channels. So physical channels are the ones which we are going to do. So these transport channels which come from the higher layers are mapped to the physical channels. For example, control channel and downlink share channel go to the PDSCH, downlink share channel. And there's something called DCI information that's generated in the physical layer that goes into PDCCH, which is the control channel. Okay, and BCH, which comes from the higher layer, broadcast channel, goes into the PBCH. So you always see the word P in front of all the physical channels. Okay? Similarly, in the uplink also, you have the PUSCH, which is the data channel, UCCH, which is the control channel, and PRAT, which is the random access channel. Fine. So again, this is also from 38.201. I'm just going to explain a little bit more. There are 2 things that happen in physical layer. One are called the channels and the other are called the signals. Okay? Channels are something that come from higher layers. They come from MAC layer as something called transport block. Transport block is nothing but a big chunk of bits. Okay, we're going to deal with that later. But so transport block is a big chunk of bits that come from MAC layer. Okay, so channels are something that always come from MAC layer. There are some things that are generated in the physical layer itself, which are called signals. They are generally reference signals and sync signals. Okay, we also saw pilots. Essentially, these are pilots. The pilots are generated in the physical layer. They do not come from the higher layers, which makes sense because they are. I mean, they are not data dependent. Okay, whereas the downlink channels, the data channel, the control channel, and the broadcast channel, they are dependent on some data that has to be configured by the higher layers. So they come from the higher layers. That's why they are called channels. Okay? Similarly, on the uplink also. The PRAT, PUSCH, and POCCH come from the higher layers. They're called channels. There's the signals which are generated in the physical layer. They're generated actually in the L1 layer. They're mainly the pilots and the synchronization signals. Okay, so you understood the difference between channels and signals. Channels always come from higher layers. They're data dependent. Signals on the other hand are generated in the physical layer. They're generally pilots and synchronization signals. Any questions?
Physical random access channel that is also generated in the physical layer. Why is not signal? Why it is channel here?
Sir, PRAT procedure has both synchronization signals as well as a channel. Okay, Because once you lock on to the base station sends you information on the PRAT channel about some things. Okay, so that comes from the higher layers. Authentication and things comes from the higher layers.
Okay.
So any questions, please feel free to stop me. Okay, I mean, I think it's good to understand this, because otherwise it becomes more and more confusing as time progresses.
Sir, when you mean channel, does it mean a frequency channel, or
No,
is it?
It's all logical bit channels.
Logical channel. All are logical channels.
Yeah, these are all bits. Okay, this is not the radio channels. When I talk to the radio channels, I'll tell you specifically these are radio things. Okay, so these are actually essentially MAC and physical layer sit on the same thing in the physical. I mean, let me just open up my. I'll draw something and show you. Okay, so what happens? So there's a physical layer, which is L1. Okay, and there's a MAC layer, which is the L2. Okay, L2 and L3 are higher layers. Okay, so what happens is, so this generally sits on your FPGA. Physical layer generally sits on your FPGA, and this sits on your computer or some processor. Okay, these two have to talk to each other. Okay, because MAC layer is the one which transmits data to the physical layer, and physical layer gives data to the MAC layer. So the MAC layer can go into the core network and other things. Okay, so this is called a channel. Okay, there's nothing. I mean, this will just be some data API. Okay, essentially this will be. I mean, this is just it's like the the 7-layer model of OSI. Okay, we're talking about a lot of layers in the OSI model now. I mean, they're technically on the same hardware, same thing, but essentially these are what we call the interfaces.
Sir, this is the FAPI interface, right? I mean,
it's the FAPI interface, but let's not talk about FAPI now. FAPI has nothing to do with it. Okay, so this gives the process, the MAC layer gives the physical layer something called transport blocks. Okay, transport blocks are nothing but a big set of bits. We'll come to that. I'll tell you how this gives transport blocks now. Okay, so channels are not RF channels. These are actual logical channels. Does it make sense, Srijay? I mean,
So yeah.
Deepanshu, please. Mr. Deepanshu?
Yes, sir. Can we say that like uplink channels are from MAC to physical and downlink channels are from physical to MAC, or both are bidirectional?
Both sides are duplex, because I mean physical layer also can't. I will come to that. Just let's open 38202. It will become clear. Just give me one.
Yes, sir. MAC is also a part of physical layer and some of the part of that layer 1. It can't go to layer 3, sir.
Sorry, sir. MAC. Can you
MAC resides on the L1 or L2. It can't go to L3.
Sir, I mean, it's called the MAC layer. So essentially, MAC layer has something called a scheduler.
Yes,
it has a scheduler. So I mean, again, it's a logical separation. That's all. Where they are physically is a very different thing. It's implementation specific. Okay. So what happens is, what it turns out is, the way the spec is written is physical layer is a dumb thing. It's a dumb physical layer, what we call dumb. All the decisions are made by the MAC layer and informed to the physical layer in terms of RRC signaling. Okay, where do you put, what to put, where to put, are almost done by the physical layer. Just blindly takes all these things, puts them in the OFDM grid, and then transmits it. Okay, on the receiver side, of course, it does receiver processing, it does all the receiver algorithms. But in terms of scheduling, intelligence, and other things, MAC layer does that. Okay, whether they are physically on the same device or different devices or all that, I mean, I will give a separate class on that. What are the new architectures for that ORAN architecture, L2, L3 architectures? I will do that later. Once we have a little bit about the physical layer, we'll do that. Okay. Okay, again, these are the same thing that are there in 38201. I just made slides for that. I mean, we saw this physical layer procedures. This one also we saw. So now in 38202, what is there? Let's open 38202. This is a very, very small document that I am going very, very fast. Again, the document number, this is 38202. This is the latest version is 15.6.0. Okay. This was made in December 2019. They generally don't change this document because this document doesn't change it. Okay, contents, scope. Okay, always the scope will be there. The present document is a technical specification of the services provided by the physical layer of 5G NR to the upper layers. That's what this describes. The references, bunch of references. Okay. So now let's just read this a little bit. Services and functions of the physical layer. General, the physical layer offers data transport services to higher layers. Essentially what this means is it takes bits from the higher layers, modulates them and transmits, receives modulated information and transmits bits to the higher layers. The access to these services is through the use of transport channels via the MAC sublayer. Okay. A transport block is defined as the data delivered by the MAC layer to the physical layer and vice versa. That's what a transport block is. So the definition of transport block is written in this document. Okay. This is what a transport block is. Okay. And then they go on to tell you what is the overview of the L1 functions, what should be done in the L1. Okay. So you should do FEC, forward error correction code. You should do hybrid ERQ. You should do rate matching. Then you should map the transport channel, the bits to the physical channels. Okay. Then you should do modulation and demodulation, frequency and time synchronization. Okay, and radio measurements and MIMO antenna processing and RF processing. This is all that should be done in the L1. This is the overview. So now they go on to tell what is the model of the physical layer. This is just a model. You don't have to implement it like this. Okay, of the physical layer of the UV. Okay. So this is the diagram in which UV is transmitting and G node B is receiving. This is the uplink shared channel information, ULSCH, uplink shared channel. Okay. What it's saying is transport blocks are coming from the higher layers of the UV. You can see my cursor. I don't know if you can see my cursor. Just zoom it up. You can see my cursor now. So the transport blocks are coming from the higher layers of the UV. Then they go to the CRC block. Okay. Then you do coding and rate matching. Then you do data modulation, which is mapping to the constellation points. Then you do resource mapping. You put in the time frequency grid. And afterwards, they say antenna mapping. There is IA50 and other things in between. Okay, generally they don't talk about all that. Okay, and control information is the one which decides all this. Uplink transmit control information. You decides the modulation scheme. What is the power assignment? What is the antenna mapping? HARC and other things. Okay, once these are received on the G node B side, you do the other way around. You go from antenna mapping, resource mapping, demodulation, coding, decoding, and rate matching, and you send it off to the higher layers. Okay. So this is a very high level diagram which just shows what are there. I mean, nothing more than that. Okay. And if there's an error, the error indicators are put onto the higher layers of the G node. Okay. You understood this diagram is a very, very high level diagram of what happens in the uplink shared channel. Sridhar, you have a question? Oh. Then they talk about the downlink shared channel. Okay, downlink shared channel, G node B is transmitting. So essentially you can see all the arrows pointing downwards and the UV is receiving them. Okay, this is a very, very similar diagram. And then they talk about the broadcast channel. Okay, I mean, broadcast channel, what happens? In the broadcast channel, is always transmitted by G node B. UV doesn't transmit broadcast channel. Okay, so it's transmitting and the UV is receiving. Okay, I think this part I don't think we should read it right now. We will confuse us. Okay, so essentially 38101 and 38102 are just very, very high level diagrams of what is there in the system. Okay? I mean, that's why I'm not spending too much time on that. Okay. So any questions? So high level, you understand what is happening. No? So essentially there's something called transport blocks that are coming from the MAC layer. The physical layer processes these transport blocks, transmits, UV receives these transport blocks and sends it to the higher layers. Similarly, the other way also happens. Okay, that's what we should do. Okay. At this point, we're going to stop since it's 10:30. From the next class is going to be the most important thing, which we'll start the frame structure. Okay, we'll start focusing on reading the 38.211 document. This is what we're going to do most of the class. most of the semester. Okay, we'll understand the frame structure. So what I mean by frame structure is what are frames, what are subframes, what are slots. Okay, what are the different subcarrier spacings? So we are going to do this in very, very great detail in the coming class. Okay, we're going to take a couple of classes to do this whole frame structure and the time resource trade. Okay. Today, I just wanted to give you an introduction on what are the documents, how do we read the document, and what does 38201 and 38202 tell about the higher layers. Okay, so the next class onwards, we'll start 38.211. Okay. So when we do this, you'll start understanding, you start relating to the OFDM that we have learned earlier. Fine. Okay. So we're going to meet again on the next class, which is, I think, is Tuesday. And Tuesday onwards, we'll do 38.211. So I request all of you to please download those documents. Okay, I'll also try to put this on the WhatsApp group so that it's easy for people to download them in case it's not, you're having difficulties with the classroom. Okay. Any questions?
No, sir. It's good.
Okay, so from now on, we'll try to relate what is there in the specification to what we learned about OFDM. Okay, that's what, why are they doing that in the specification? That's what we try to reason. Okay, one thing is reading the specification. By the time at the end of the class, end of the semester, you will be able to comfortably read any spec document and understand that. That's one of the goal. And the second goal is to understand as much as possible on why they are doing what they are doing. Okay, some of them we don't have answers. I mean, there's a lot of history to this. I mean, some of them I don't know. I'll try to find them out as and when. Every time I teach a class, I learn something new. Okay, this class also won't be an exception. And we'll also try to figure out what is happening, why they are doing what they are doing. Okay, these are the two main goals of this semester. Okay. Okay. And of course, we are also going to implement. So I'm hoping that all of you are getting a little bit comfortable with MATLAB. Please, at any point you are having any troubles, please let the teaching assistants or me know. Then we will, if the extra classes are required for MATLAB, I will take care of that.